Hello, this is Michael, and today we're checking out Create Power Grid, which is one of the best Create add-ins in my very subjective opinion, because it adds realistic electricity, sort of. Now let's dig right in. So, with real-life electricity, we have three of the main uh, properties, which is voltage, current, and power. Power is current times voltage. And voltage is the difference between two electrical potentials, which means, in simple terms, it's how much the energy wants to flow from one point to another. While on the other hand, current is the amount of flow that's flowing through something. If we add two voltages together in series, (16 and 16, for example, they add up. If we add them in parallel, being they are the same, they stay the same, but the current increases. Now, as you've seen, it burned when I set it to 0, because the voltage is the difference between potential. So it was as if I was short-circuiting the 12 volts to 0, like this. Now, most devices in this mod have a polarity, plus and a minus, negative and positive. And for things to work correctly, you have to adhere to this polarity, otherwise it would show negative voltages. And in case of motors, they would spin backwards. That's how I reverse motors. Okay, so let's get to resistance. Resistance is the fourth of the basic values you have to look for, and voltage is driven by Ohm's law, which says that voltage is current times resistance. Resistance has the unit of ohms. And knowing this, we can manipulate voltages by using different resistances. For example, this is an example of a voltage divider, which is a circuit that divides a voltage into two different voltages. As you can see here, we have a current of 1.8 amps going through this divider, and knowing that current, we can calculate the voltages on each of the resistors. Next, let's tackle the two most important laws of electronics, which is the Kirchhoff's laws, which state that energy, it's basically a laws about conservation of energy. For example, the first law talks about current, where what goes into a net has to go out of a net. Here we have an example of current going through parallel lamps. As you can see, the more lamps I turn on, the higher the current. However, if we put the lamps in series, they won't turn on because the voltage is too low for them. But the current does increase. Next up is the rheostat, which is a variable resistor. We can use it to limit current or divide voltage variably. You can also change its maximum value using the slider on the side. And then we can move on the last example with the Ohm's law and Kirchhoff's law, and that is how to choose a resistor for a given circuit, for a given load. Here we have a 24 volt source and two 12-volt lamps in series, they light up no problem. But if we would put down a light bulb, a 12-volt light bulb on its own, it's going to blow up because the voltage is too high for it. Now, to make it work with just a single light bulb, we need to choose the right resistor to drop the voltage to half. That means the resistance of the resistor has to be the exact same value as the resistance of the bulb itself. And to know what the resistance of the bulb is, we may use the shift function to see the rated voltage and rated power. Now, using the formula on screen right now, you can calculate the equivalent resistance of the light bulb. Now, keep in mind, light bulbs have a lower resistance before they heat up. Meaning, it may not be at lower voltages where it's not lighting up, the resistance might be higher than the one that's calculated from the power. That's why it's called equivalent and not the actual one, because that one depends on the heat of the filament. Okay, let's go on the way you connect things together, which are four types of wire this mod offers. First one is the uncoated copper wire, second one is the gold wire, and the third main one is the iron wire. Now, for the copper one, it has the lowest resistance and the lowest power capability with a range of 16 blocks. The gold one has a range of only 8 blocks. It can take 160 amps, which is double, and has a double resistance as well. And lastly is the iron wire, which has the highest resistance, but takes the most takes the same amount of current as the copper one, and has the most range. And lastly is the insulated copper wire, which works exactly the same as the normal copper wire, with a slightly lower current rating, which is great for organizing your cables. Okay, now let's get to the second device, which has a variable input, and that's the adjustable transformer, also known as the variac. The difference between these two is the one changes the resistance, the second one changes the ratio of the input to output. For example, here it's 1 to 737 to 1, which means the voltage should be halved, which it is. So you can much more exponentially decrease the voltage. On the other side, the rheostat is more linear. Okay, so let's get on to how we actually make power in this mod. This is just an example, so I will dig into generators later. Basically, we have it's a mix of a synchronous generator and a DC dynamo, because this mod doesn't have AC current, it only has DC, because you can simulate only at 20 Hz. So the developers have decided to make a balance between AC and DC, having it have the having the easy current and power calculations of DC, while having the ease of changing voltage with AC using transformers. With the same parts used to make generators, you can make motors, which can be used to power your creations. Here's an example of a network where you can see some of the devices the mod offers. This is an example of a generator that's using a carbon pile for regulation. I'll get back to these when we get to designing generators. As you can see, the voltage is 140 volts. Using a plotter, you can plot your voltages and have a nice history. This one is going quite fast, but if we slow it down, you can have a pretty long history, up to, let's see, 7 seconds I can see over here. So you can play around with that to make like a chart of how much voltage you have available. So first of the devices we can look at is the electric fan, which works just like the mechanical fan, but you can add a heater to make it cook items. And also, yeah, it's just an electric fan. There's not much to it. You can use it to cool devices. There's also the pyramidal of heat, as you can see. If devices overheat, they explode. So next up is the motor. It's pretty self-explanatory. You give it power and it spins. The constant speed motor maintains the same speed at any input voltage, although it loses stress units. And lastly is the servo, which requires a 0 to 5 input to set the angle. This is useful for creations you need to control precisely. And then we have the lights. The light bulbs is pretty simple. You give the power and it turns on. We have contactors, which you can use to control different circuits with each other, using a lower voltage to control the contactor. Over here you can see I have to put a resistor of 20 ohms for it to work. And then we have the bell. Again, I had to lower the voltage using a resistor. The electromagnet, which is used to make magnets. It takes quite a bit of power, so I recommend... Oh, and it heats up a lot as well. So this is used to make magnets, which are used to make motors. Useful thing. So this is an example of how you could use your for your power. There's also the electric basing here, which can be used instead of blaze burners, although it does take 5 kilowatts of power for the highest stage of heat, which is a blue blaze burner. And let's see what's the minimum for the first stage is around 3 kilowatts, which is still a lot of power. Now these thicker wires you can see connecting to these plugs and sockets and junctions are called cords, which let you carry two wires using a single cable, which is pretty neat. You can also use these string lights, which are very sensitive to voltage and provide a little bit of light power. Now, how do we distribute our power through our world? This is a very simplified example of a power distribution system. Here we have 120 from a generator that gets stepped up by a transformer, transferred over a long distance, and then goes through a circuit breaker which protects the second circuit from short circuits, and a spark gap which protects it from voltage surges. And from there it goes to a transformer that steps it down back to 120 volts. So, to turn on a breaker you have to first load the spring and then give it a redstone input. As you can see, it turned on, the lights are on. If we were to have a voltage spike, as you can see, the wires didn't like that. Let's put it back down. The spark gap activates and it trips the breaker. Now, if we were to have a short circuit, the breaker activates and disconnects the circuit. You can set the current of the breaker using this slider. And lastly, the last device I want to take a look at is a carbon pile. Now the carbon pile is a resistor that's controlled by current going through the carbon pile coil. So we have this motor connected through the pile. You can see the resistance is quite high, so it's not spinning. If we increase the current going through the pile, or decrease the current going through the pile, we get a higher voltage from the motor and it starts spinning. So this is the basics of the mod. This is what it can do, and this is what it's for. Next up, I would like to take a look at generators. So for designing a generator, we have to understand what are the values of its components. For example, one of these coils for the winding takes 0.5 ohm per one, and one of the rotor pieces has 0.5 ohms. This means we would rather extract energy from the rotor than from the coils, because the lower the resistance, the higher the current we can provide. This is an example of a small generator, one of your starter generators. And here I want to demonstrate the importance of saturation current. The saturation current of the exciter coils, as I call them, because they are what creates the magnetic field for the rotor to work, is 2 amps at a maximum of about 4.5 amps before they explode. So to wind a generator, you need to use a shaft and a copper coil, and use it like when you're building belts, like so. Now these shafts have to be pointing towards the rotor, and in case of having 2 windings like this, you have to use at least 1 generator housing to connect them together. They will be connected in series. This means the resistance will increase. So let's start it up. As you can see, as it spins up to maximum RPM, the current going to the coils, as you can see here, connected by a device connector, which is an item you can make, used to connect most of the devices, has 2 amps precisely. And this is generating 360 volts at 4 kilowatts, which is quite good for a starter generator. And now the circuit for the exciter coils is just a rheostat connected in series with the minimum resistance set to 200 ohms. So we may adjust the current flowing into the coils by adjusting the rheostat. If we go below the excitation current, the power drops. If we go above, we not only start wasting power, but our power also starts dropping. So keep in mind, keeping the exciter current at the current value is worth it. At the correct value is worth it, because it keeps the generator stable and producing maximum power at minimum losses through the excitation. You can also put rotors next to each other to produce more power and more voltage, because if you put in series, the voltage adds together. And in this example, we have to step down the voltage from the generator to feed the exciter coils. Again, the same setup, rheostat in series, set to around, this one is around 1000 actually, because the voltage is higher. And then we step it down to 120, and we can connect as many loads as you want. Again, this one is going to be generating around 3 times the amount this one is. So it could be around 10 or 12 kilowatts. I would bet on the latter, a smaller number. Now to build the generator, you only need the generator clutch, the commutator, which is where you take the power out, and the rotor windings, and the coils. And as I said before, you connect them together with the housings. Now for the best generator you can design, we can take a look at this performance test where I did the math. Over here we have 3 generators, 1 by 3, 2 by 2, and 1 by 5. And they are all saturated at the correct current. Yeah, fully saturated, 2 amps. And I measured the power they make and subtracted the saturation power lost. Now, comparing these, I've discovered that the 2 by 2 is the most efficient with only 2% loss, and the 5 by 1 being the least efficient. So the more commutators you add in series, just on a flat line, it's not gonna do you very well. Now over here it's connected in series and in parallel, because it's the simplest way to wire it up. You can put them all in series, the It's the same power, just different voltage. And it's producing around 41 kilowatts with around 1 kilowatt of loss, giving you 40 kilowatts of total power from one of these. This brings us to a demonstration with something more exact, which is this kind of power plant, where you can imagine your source of rotational power powering this generator, which then gets through a transformer fed with a saturation current. You can see 837 volts from 1700 volts. We take the 1700, we step it up, add a breaker to protect it from short circuits, and a high voltage switch to disconnect it if we need to service it. Now I'll quickly make a little adjustment because the mod isn't 100%, it's still in beta, so I have to reconnect this to have it work. And we have 7.2 kilovolts on this line. Now I've did this measurement using a voltage divider and using a tag on any gauge from this mod, you may change the way it is displayed. So here it is multiplied by the division of the voltage divider, and I turned on the unit prefix so it adds the kilovolts at the end. So yeah, when you have your power, you can make your own substations which can step it down and power your devices. So let's turn on the main breaker of this power station, which has 3 transformers, one for each type of load. Here we have the light transformer, which gives you 120 volts. It's, just a 1 amp breaker. And here's the gauges measuring the current coming through the breaker. And over here we can see that there's lights connected to it, everything's fine. Cord lights, and in case we overload it, the breaker acts, disconnecting the circuit. Now let's say we make a short circuit on the main breaker, I think. This is just the light one. But the current was high enough to trip the main breaker. So this is why I have a main breaker and the other ones. So you don't trip the one at the generator. Now lastly, the type of load you can have is a multi-block motor, which should not operate at the maximum RPM because it will break. You have to run it at 255 or 254 and step up the rotational speed with a rotational speed controller. It also loses speed with load. So let me show you this example of a motor. Again, it has a breaker and its own transformer. It takes more current to spin up, then it goes down, and then the current becomes dependent on the load you put on it. Meaning the more load, the more current, and it slows down as you can hear. So yeah, these are the motors. Same construction, same rules with saturation. I've been talking a lot about transformers, which are these little neat things. They used to change the voltage while keeping the power. Well, not really. Okay, they used to change the voltages of your lines. Now, there are 2 transformers. You make them by wrenching transformer cores. The big one is the 2x2 and a 1x1. 1x1 can only hold 60 windings, while the 2x2 can hold 240. And using the different proportions of the windings, you can change the voltage on the output. You can increase the voltage or decrease the voltage using a step up or a step down. And how much power you can get through a transformer depends on the number of windings. Here's an example of a 1x1 transformer with different numbers of windings with the same ratio, and you can see that the power is much different. The more windings, the higher the resistance. which is calculated like this. And it's the so-called parallel resistance. And this limits the power you can send through the transformer. So this one's the 30 by 30 can only send 81 kilowatts. Well, this 10 to 10 can send more than 24 kilowatts. Here's another example of a distribution setup. We have a step up and a step down to power your device. As you can see, this one is 80 kilowatts because the ratio is 1 to max, and this one is the opposite, max to 1. And we get approximately, again, the voltage may be a bit higher, but it will drop down as you load it. Again, there's a voltage divider and a custom display. Now, I've been using a lot of circuits in these examples with the voltage dividers. So let's get into how to make circuits. So basically you start with You start with the schematic of your circuit. So to design a schematic, you need this circuit design table, which is made like so. And to know which parts to add to a circuit, you use $sign. Oops. $sign. $sign component. NJI. Here you can see all the components you can put on a circuit board. Wire connectors are used to connect them together. Copper nuggets are used as vias, which can let you connect the two sides of the circuit board together. And resistors are resistors. Diodes work as diodes. It's a one-way sort of. It conducts electricity only in one way. We'll get more into details later. First, how do we make these? Well, we start with the schematic. Then we apply a wooden board, add some dough, and a copper sheet. Do this a couple times. Forgot to press it. You do this twice for each layer. And then you etch it in acid, which is made by mixing redstone and blaze powder, I think. Let's see, acid bucket. Yep, blaze powder and redstone. After you etch your circuit board, you may put your components on it using a mechanical arm. This one has no components, so we cannot put anything on it, but that's how you do it. Okay, so what can you do with these, aside from smaller voltage dividers? Well, the simplest and most useful is a relay. It works as an electrically controlled switch, which has two contacts, normally closed and normally open, which allows you to switch between two outputs. Here I have a red and a green LED, which is controlled by this lever. Here's an example with a single light source controlled with by two spaces. Here's the same thing but with three, where we use the double pole relay, which has two sets of contacts to cross the wires. And we can also use them to make logic gates and memory. And also all sorts of cool stuff like the sign. Where we also use the capacitor, which is a device that can store energy. And to drive motors. And most interestingly, you can also use the redstone relay to interface your circuits with vanilla redstone components and modern redstone components, of course. So you can use a voltage gauge to output redstone signals, and a redstone relay to input redstone signals into a circuit. Moving on, more complex components of a circuit board are the switching elements, which are the electron tube, the SIT transistor, the NPN and PNP transistors, and that's pretty much it. So the electron tube works as the ponder says. We may control the flow between two terminals using the voltage on the grid while having to heat the heating element, powering the heating element, which lets us control higher voltages with very low voltage. The worst thing about these is the kg variable, which is the minimal resistance it can have, which is usually it's minimum 200 ohms, which is really bad. That's why it's more useful for higher voltages. Here you can see I'm using 155 volts to compensate for the loss to get 120 on the bulbs. Next is the SIT transistor, which works similarly to the electron tube, with the exceptions of having no heating and having a lower kg value, but a lower power and lower voltages. We may use it to control this bulb, for example. This is just a simple switching example. And then there are the transistors, which work, again, using a current. I forgot to say, this is also using a current, which is the same, but you change the voltage. Here the current is different every time. It just multiplies the current by the gain, and that's what you get on the output. So this is the NPN, which is controlled by a positive voltage and a positive current. This is the PNP, which is controlled by a negative current and a negative voltage. It has to be, as you can see now, it's 12. If it's less than 12, it turns on. Using these, you can make all sorts of circuits, like this voltage comparator, which lets you compare two voltages and turn on light depending on which one is greater. Or voltage stabilizers, which let you control the output voltage up to a certain power. This one is only 10 watts, which means 3 light bulbs is all it can take. Here you can see the voltage went up a little, but when you put the light bulbs back, it goes down. You have to change it with this trimmer, this potentiometer. Potentiometers are like rheostats, but smaller. So yeah, let's get to the variac. I mean the varistor. Varistors are resistors controlled by voltage. The easiest way to demonstrate this is with a crowbar circuit, where you have a 160 volt varistor in parallel with a bulb that's in series with a fuse. Now in case the voltage spikes, this guy, the varistor, short circuits the fuse and protects the light bulb from exploding. If it returns to normal and reset the fuse using an iron bar, you can restart the circuit normally. Another use case of these is to control the voltage, control the saturation to regulate the voltage on a generator, so you don't need to transform it. I think this example blows up though. Hold on. Oh no, it works. Yeah, it just blows up. There needs to be resistor in series with this for it to work precisely. So yeah, here you have around 120 volts. It's gonna stabilize. There it is. And now if I load, it's gonna stay around 120. It went down, but now it's going to recover. It takes a while. There we go. So that's another example of these varistors being used. It's a pretty cool component, pretty essential. Now to the extra bits and bobs, and that is the punch card reader, which is a way to control multiple outputs in a sequence. Like the relay, it has a common input and 4 outputs, which are normally open. Inserting a card using a sequence controls the outputs in that sequence, so you can regulate the speed. By regulating the speed, you turn the kinetic input at. If you reverse it, it's going to play the sequence again in reverse. So yeah, this is the extent that I know the mod at. What else to add so I can cut it somewhere in the middle, splice it in. I don't know. Oh yeah, series versus parallel. Going back to this. So yeah, this is what this mod has to offer. This was a really quick rundown of all the features and use cases of the systems in this mod. It's really useful if you know something about electronics prior to getting into this, because it's pretty complicated. Although it's very nice to see something like this in Minecraft. So yeah, I hope you enjoyed this quick video, and I hope to see you next time. See ya!